Hello, uh, hello, hello, hello. Board coming in a second. Hello. Board is coming. One moment, please. Okay, hello. Oh, wait. Okay, good afternoon. Oh, wow. All right, awesome. Let me get this party started. Hello, all right. Hello, Claudia. Hello, Paulina. Hello, Josephine. Hello, Alan. Hello, Eric Logan, Shy, Katie, Alexis, and Jada. And now to chat. Hello. Where is it? Good afternoon, Shy. Hi, Victoria. Victoria. All right. Good afternoon, Stephanie. Good afternoon, Jenna. Good afternoon, Shirley. Good morning. Morning-ish, Nancy. Hello, Josephine. Good afternoon, Alan. Afternoon, Eric. Good afternoon, Alexis. Good afternoon, Emily. Good afternoon, Logan. Wow, this is a big. Good afternoon, Paulina. Good afternoon, Maria. Good afternoon, Katie, who was here like 20 minutes ago. I'm aware of that. Thank you. And good morning, Jada. And Jada was here a while ago. Okay. Hello, everybody. We're gonna just get I'm trying to go take less and less time to get to business. Um, sometimes I actually do see these YouTube videos and they're painful, how long it takes for me. Okay, so we're gonna get to business, couple of announcements. So we have class right now, just to be clear, in case there's any confusion. We have class. Thank you for being here. We're going to do stuff. Then today, the other class will not meet synchronously. There's a reason I'm telling you this. They will not meet. They will watch the video of your class. Why should you care? Just because, in case you think that's unfair or something, we're going to flip, like next week or the week after, we're going to flip that arrangement. You'll get noticed, but there will be a day in a week or two where you don't come to class and you just watch the video of the other class, just so you know. Sometimes we do that. That's what do they call synchronous, asynchronous, mixed, whatever. Okay, that's number one. Also on that note, I think I made an announcement to this effect. Last time we had class, last Wednesday, you did the same thing as the other section for most of the period, but then at the end of the period, I made a decision.
Hello, Professor.
Hello, good to see you. Thank you for saying hello. Hello. All right. Good to see you, Shawnee. Or hear you. At the end of last class, in your class, oh yes, in your class, we did an example problem of how of how um of how to use the fact that sometimes when acceleration is a constant, when and only when acceleration is a constant, then and only then average velocity does equal the average of the first and last instantaneous velocities. This is going to come up again and again and again. I'm not trying to re-explain it at the moment. I'm just trying to remind you, and put another way, when and only when acceleration is a constant, the average velocity for a whole interval between 2 points in time is the same, double equal sign, is the same as the instantaneous velocity right in the middle of the time, i.e., when and only when acceleration is a constant, the mean velocity is the median velocity. Okay, now that's like a mouthful, and honestly, that is not either of the two equations that's written on the board here. It's the equation that we established at the end of last week. Probably in a couple of minutes, I'm going to write a list of all the equations for you, or very soon I'm going to, so we can keep them straight. But just because it's been a whole week, actually I am going to write it right now. Hold on a second, just so you know what I'm talking about right now. Okay, the equation I just wrote here was the conclusion from last week's class. It's a new equation. It's a very subtle equation. In some ways, it's more sort of dimensional and complicated and easily underestimated than any of the equations we have before it. I don't want to go into the whole discussion again, but I just want to remind you, this is the most recent equation we established last week. And one of the things that's most subtle about it is it's our first equation that is not a triple equal sign. It's our first equation that's a double equal sign, meaning all the other equations we have so far are always true, even if they're not always useful, or even if you don't always know quite how to use them or something, still they're never wrong. All the equations, they're all definitions, all the equations we got before this one. This is the first one that's only true under certain conditions. What are the conditions? The condition is what's written here on the page, that acceleration has to be a constant, right? Now, again, I'm going to like summarize and review all these equations sooner or later, but just to remind you where we left off last week, this equation is our new thing. In short, it says that when acceleration is a constant, then the mean velocity is the median velocity. And frankly, put it even better way, under this condition, then the average velocity for a whole interval between 2 points does equal the instantaneous velocity right at one certain point, the point at the middle of the time. So this is the equation that really allows you to get from an average to an instantaneous. It's really important that way. And it's the first equation, honestly, I'm going to say too, where like almost whenever it's useful, it takes practice to realize that it's going to be useful. Like, I think so far out of all of our equations, it's the hardest one to even think to know when to use. I'm just admitting that, just so you like look out for it. So, okay, but we're going to practice it and use it a lot, of course. But this is my long way of saying, and obviously, if you already have any questions about it, or you remember having a question at the end of last week, definitely ask me. But the thing is that at the end of last week, at the end of last Wednesday, in your class, we did a fairly quick practice exercise just to sort of demonstrate how this thing works. I know I did it quickly, but it's in your notes. You know, it's worth just referring to as a first example or practice exercise. However, in the other section, I just want to remind you, if this wasn't already clear, in the other section, I told them to watch your video of that and I gave them your PDF or whatever, or left it in their PDF. But in the other class, instead of doing that, I derived a new equation from this. And I believe in the Google Classroom, I asked you to watch at least that part of their video. I hope you did, or if you didn't, please do soon. Or if there's any confusion about this, let me know. But I believe I did link you to that other class video, and it's only a matter of like a 20-minute difference or something. But there's the conclusion that I came to in the other class. So I'm not going to redo the whole derivation now, but the conclusion is this. Okay, this thing in brown right here. So this is yet another equation. Now we're starting to have a lot of equations, right? And this one also. So I'm not going to redo basically what I did algebra on all the other equations that we have so far. I put them all together algebraically. That's okay. So you can review that or look at that if you want a proof of this or you want to see where it came from. But as far as what it does for us, or what its use is, or what its meaning is, well, its meaning starts getting practiced and used in that homework that many of you just turned in, and many of you just got a whole bunch of points on. And of course, the rest of you still can turn in. This equation here at the bottom, just to review, two things about this equation at the bottom to add to your list or whatever. First of all, this equation is also, well, here, okay, let me say some comments about it. So again, what I'm skipping right now is exactly how I algebraically got it. Oops, sorry. But I mean, what I did was I just took the other equations that we have so far and put them together. So, and of course, you know, if you took physics in high school, I imagine many of you recognize this. That's fine too. So let me make some comments about it. Okay, comment number one. I don't know if I just lost someone to the chat. Okay, comment number one. That someone's here. This equation was derived from the other, three of the other equations we have. One of which was the V bar, the new one, V bar equals V naught plus V over 2. So, and that new one, the V bar, I just made a big point of saying, like, assumes that acceleration is a constant. Therefore, this one that I just wrote down, since it's coming from that, this one also assumes that acceleration is a constant. It assumes that you have some value for A that's not changing that you can plug in here. Okay, so this is known, this and this are known as constant acceleration equations. That does not mean that they are equations that necessarily solve for a constant acceleration. It means that they are equations that are only true if there is a constant acceleration. Okay, so that's number one comment. Like this one and this one are constant acceleration equations. Okay, number two, and obviously we're going to start practicing in a minute, or we're going to see how it works in the homework that you had. Number two. Okay, just to be clear, because especially sort of to prepare us for physics 204 and other things to come, this equation x equals v, this equation x minus x naught equals 1 FAT squared plus v naught t. And by the way, again, you may have seen it in high school, you might write it slightly differently, right? Like you might have, and you might want to make a note of this, like I have x minus x naught equals blah, 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 because I'm just trying to say the displacement equals blah, 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 blah. In high school, you might have seen the x naught written on the other side. Like you can add x naught to both sides. That's perfectly fine. And there's good, and it's perfectly correct. If it looks better to you the other way, that's totally fine. There's many ways in which the other way does look better in a way. But I'm writing it this way. But either way, if you look at the equation, it looks sort of complicated. But it's a very standard equation. It's very important. because what it does, it's sort of the first, it's the first equation we have now, or the fundamental equation we have now, which, assuming a certain set of conditions, like assuming a acceleration as a known constant, assuming initial velocity as a known constant, this equation takes time as its input and it spits out final position, i.e. displacement, as its output. This equation says if you name the when, I can name the where. That's always what we're trying to do in physics. We're always in physics trying to say where something is going to be when. Like, it really, honestly, every question in physics reduces to this issue of, if you name the time, if you name the point in time, can I name the point in space of some object, or vice versa? If you say, I want to know when the object is going to be 3 feet away, right? That's physics. By the way, that's classical physics. If you're using physics to to solve crimes, forensic physics, right, or criminalistics, then the only difference is that you're probably looking in the past rather than the future. You're asking, hey, if the bullet landed here then with such and such speed, where was the bullet 5 seconds ago, or whatever? Where did the bullet come from? You know, who shot the sheriff? That type of thing. So what I'm saying is, anytime in physics that we get an equation that takes in time and spits out position, that's really what we're looking for in physics. And the only reason we have more than one equation in physics, or the only reason you have to take more than one class in physics, or that physics goes on and on forever, is that what we keep doing is testing different conditions, or considering different conditions under which someone would ask, given the time, what's the space? So this is so all such equations that take in time and spit out position, are known as position functions. This is a position function. Strictly speaking, it's position as a function of time, like function in the mathematical sense of the word, right? Like input, output, right? All that. So it's very, so if you remember it from high school, or you remember whether you liked it or not, if you remember coming up a lot, the reason is this is our first fundamental position function. It's treating t as the independent variable. It's treating x as the dependent variable. And to be clear, to say this one last time or one different way, everything else in the equation, a and v naught, and even x naught, if you like, are all constants. They're not variables, they're constants. And if it's still a little bit confusing to you, which it may be for some of you, remember x naught just means wherever some object started. If and when possible, if we can, we set x naught equal to 0 when we can. We make our life easy. Often x naught is 0, but not always. Often, okay, but often it does cancel out. Okay, so that's the deal with that equation. We're going to use it now in these practice problems. Yeah. I'm going to start talking about the homework now. But again, I know, of course, it was another leap forward. And I know we all, we didn't have school for a while. So many of you handed in and got a ton of points just for handing in. Many of you still have to hand it in. I understand all that. That's all fine. But because we're still all working on it, and some of us are still catching up on the old. And by the way, I think I promised this before. It's definitely true now. You definitely, what day is today? We keep not having. Well, I didn't post any new homework yet. Let me just put it that way. I may or may not, but right now you don't have any new homework posted. Can I go over it? Is that what you just, wait, someone just said something in the chat. Hold on, where did the chat go? One second, I saw something in the chat. Oh yeah, okay, can I go over 3 and 4? Funny you say that, because I was definitely about to go over something that wasn't number 1. So I think Claudia, you may be on the exact same page as I am. Let me see what I was about. 3 and 4. Oh, wait, 3 and 4. Are there 2 things named 2? Oh my God, why a 1? Oh, I see. 2, 3, and 4. Okay, so the answer is okay. See, if you're talking about what I think you're talking about, Claudia, the answer is definitely yes. I definitely will. Those are definitely worth going over, and I will. I'm actually going to start. There's going to be one that I want to do. Well, actually, no, maybe I will just start with it. I was going to start with page one, I'm not going to do the warm-ups right now. That I can tell you. We can go back and I can give you answers, but I'm not going to do the warm-ups right now. But number 2 with the baseball, I want to quit. Number 2 with the baseball. So again, I hope you're all with me here. I'm on Big Old Duck homework. I think it's homework 5. And again, I don't, whether you've done it or not, that's what we're talking about right now. I'm skipping number 1 for now. Those of you who haven't done it, do that. Number 2 in Roman numeral 1 about a baseball rolling down a 6-foot slide. I want to do that quickly and then get to the thing Claudia is asking. I want to do it because I think it's a good review, whatever. But also, I'll just caution you that this one, number 2 with the baseball that I'm going to do sort of quickly, it's kind of an expansion or an extension of exactly how we ended class last time. So hopefully it won't throw anybody. But all right, let me just look in the chat if that's okay. But yes, I mean, the answer to Claudia's question is yeah. Oh, yes. And then someone, oh, wait. Yeah, same, Alan. Okay, I see. What? And I'm just confirming, Claudia and Alan, you mean, yeah, oh, and all of you. No, we're going to go over all, like, I promise. I mean, this is worth going over. It's just a question of which one I do first and how much I get to today. But believe me, and I think you're probably not going to get anything new for a little bit, probably, but yes, I'm definitely going to go over it. And I do appreciate this feedback. One thing, I'm assuming that Claudia and Alan and Eric mean Roman numeral, like you wrote Roman, you mean the Roman numerals, right? I assume you do. Okay, but yes, I'm going to, definitely. I want to quickly do the baseball one first, but then also there's one other thing in the chat. Oh yeah, Roman numerals. Okay, great. Yes, thank you. Okay, awesome. Quick thing to someone asking the direct chat, just to reinforce again, like, yes, you can still hand in the homework. Everybody can still hand in the homework. The reason you want to hand in the homework on time, the reason it's better to hand in the homework early is you get points faster, you get acknowledgement faster, and you just don't fall behind. The idea behind the homework, the ideal is that you try to do it, you try your best before I start talking about it, because then it makes class much more, like, then you know what you're looking for to get out of class and all of that. So there's a lot of reasons to hand in the homework earlier on time, but yes to everybody, that you still can turn it in. Absolutely. And it's not a matter of penalties. It's just a matter of when you get the points. Okay. I hope that's clear, but okay. No, yeah, no problem. No, that's definitely the deal. And okay. So I want to honor what Claudia and other people are saying. I'm going to quickly, bear with me though, or forgive me. I want to quickly do Roman numeral. So this is homework number 5. I think it's 5. Big Old Duck. But yes, the homework's getting thick now. Believe me, I think so. I think this is getting worth thinking about and talking about. So for sure, we're going over at least the thick ones. Yes. Okay. Whether I do the 5-step method or not is a question. But anyway, 1, 2. I should have given it a title, but this is the baseball one. Okay, I'll try to. Okay, so I'm going over number 2. So stop me if you don't know where I am, but I'm on Roman numeral 1, number 2. Okay, so here's the deal. I guess I will do the 5-step method because I kind of have to. And someone's here. Sorry. Okay. Okay. So I'm doing Roman numeral 1, problem number 2, the one about a baseball. Here I have my step 1, my diagram and fact pattern. Now your diagram might look very different. Your slide might be going to the other way. That's fine, but mine's going this way. I'm calling, now notice this, I'm labeling my coordinate system. and this is a little bit unusual because I just happened to make the slide go to the left and down, which I didn't have to, but I just happened to. I'm calling down positive. You might think that's a little unusual. It is a little unusual, but since this ball only travels down, since it never travels up, I want as few negative signs as possible. So I'm calling the direction of travel positive. You see what I'm, right? Like that is, oh yeah, we're definitely not going to have new homework due. Okay, we're definitely not having new homework because I still have to go over train of thought. I just remember, right. So just catch up over the next 5 days, okay? I mean, I'll put that clear in Google Classroom, but just catch up with everything, and so will I. But anyway, so notice I'm labeling the downward direction as positive, and that's on purpose. I don't have to. I could make down negative, but I have to make something positive and something negative. And I think it's much wiser and more convenient. It's going to be easier on me if I make the direction of travel positive, because then I won't have any unnecessary or extra negatives. I'll have as few negative signs as possible, i.e. none. So I'm making down positive, and I'm making that clear in my diagram. Also, it happens that I made my ramp go to the left. That wasn't really a conscious decision, but I did. So therefore, to the left is now positive, right? Because down is going to the left. So that's fine. Just get used to the idea, like as long as I've labeled it and I stay consistent with it, that'll work. I've labeled the very first position that the ball is at 0 feet. And then the very last position gets to 6 feet. So its total displacement is 6 feet. 6 feet, right? And I've, put in the information that the whole thing, according to the problem, takes 2 seconds. Okay, so that is my diagram. In fact, pattern. That's my diagram fact pattern. Okay, I'm just going to change the view on the screen. Ooh, a lot of people coming in and out. Okay. So then question. I think there was 2 questions asked in this question. Yeah. So then question A, the question is at V equals 3 feet per second, T equals question mark, right? That is the question of A. So that's my step 2, WIQ. What is the question? Right, that's my question. Now, I don't know. I mean, I do know, but like, what should I do? This is like a weird, like it's asking about instantaneous velocity. Instantaneous velocity is kind of one of our new concepts. I think it's a harder concept than average velocity. I keep saying that. Instantaneous velocity means velocity at a point. That's a more precise idea, but it's also a harder idea to picture and to calculate. Technically speaking, what we're asking for is a derivative here. We're asking for derivative of position with respect to time. Like all that's true. But for some of us, well, that's all true. But I don't know if any of what I just said is going to solve the problem for me. Like it's not obvious to me how right off the bat how to get instantaneous velocity. This is where step 3 GDP comes into play. Like I might not know how to get to the answer here. In fact, maybe I do, maybe I don't. But but it's not obvious off the top of my head what the answer is or how to get there. What I should do, instead of trying to work backwards from the answer, I should try to write down things that I think are definitely true, general definitions and principles. So here, to get into the mindset of what the mindset that we might have if we were taking an exam or something, this thing is asking for instantaneous velocity. It's not asking for average. So what I might do, I don't know if you did this or not. I'm not saying this is the only thing to do. What I might do is say, well, the new concept that we just learned recently was instantaneous velocity. And well, here, you could write it one of 2 different ways. The instantaneous velocity is average velocity taken to the limit as time approaches 0, right? In other words, what instantaneous velocity is the derivative of position with respect to time. Now, I'm not trying to trick you. Like, I'm trying to assume for the moment, I'm trying to teach you what to do if you don't know what to do. If you already know the answer, cool, fine, just bear with me anyway. But like the whole goal of this class really is for us to learn what to do when we don't necessarily think we know what to do. So one thing I might do is write down the definition of instantaneous velocity, which I just did here. This is like one of our new equations. It says that instantaneous velocity is a derivative. So I write that down. Say this were an exam right now. I would write that down and I would get points for it because it is definitely true. It's a triple equal sign. It's true knowledge and it's topical. So I would get points for it. Now, to be fair, and again, I'm saying this, I'm not trying to trick you, but to be fair, I don't really know what I can do with this now. It says that velocity is a derivative. That's true. But something that confuses people a lot is like, what do I do with derivatives? Like, I kind of know how to take derivatives in calculus, and I kind of understand that this thing is a derivative, but how do I like use this equation? Well, that's a good question. In order to take a derivative, I want you to understand. Well, here we, yeah. Okay, I just want to be clear. Again, I'm not trying, well, if you want to take a derivative is not something you do to a number. A derivative is something you do to a function, right? A function is number in, number out. A derivative is an example of something called an operation. A derivative is not number in, number out. A derivative is function in, function out. In order to take a derivative of x with respect to t, we would need some kind of function which takes in t and spits out x. Now, we weren't given that here. So I'm just trying to say, actually, this equation that I just wrote down is true, and you would get points for it on the exam. But then if you started realizing, oh, wait, in order to actually take a derivative, I would need an xt function. Well, then you might realize, okay, that this is not going to work for me. I got to write down something else. And that's fine. That's what I want you to sort of get in the habit of being willing to write down things as you go and try things. And what I'm not going to do now is say, oh, wait, this is totally wrong, and cross it all out and go and erase it and go in a new direction. No, I've written this down. It's giving me some knowledge. It's showing me that I need something more to do this problem. So I'm going to go a different direction. I'm going to say, well, since I can't take a derivative, since I can't directly get instantaneous velocity, I'm going to write something else down that I absolutely know to be true, even if I don't know what I'm going to do with it yet. I'm going to write down that average velocity equals displacement over time, like the same thing we've been writing for every single problem so far, right? Even though this problem is asking for something new, I'm going to, instead of writing something relevant and trying to make it true, I'm going to write something true, always reliable like this, and see if I can make it relevant. Well, here I go. Wait, hold on. Okay, yeah. So I'm writing this down. I'm also going to write one other thing before I start plugging in numbers or whatever. Like, this is a true statement, right? Also, the problem. Also, the problem says that acceleration is a constant. It says it. It doesn't tell us what the acceleration is, but it tells us that the acceleration is a constant. Therefore, what we also know here is that v equals v naught plus v over 2, that new equation that we derived yesterday, right? Okay, I now have two equations for average velocity. They're both relevant to this problem. How? Well, now I'm going to go to the problem itself, step 4, PAW. I'm going to start plugging in now and show you what I mean. Here, here, x minus x naught equals 6 feet, and t equals, I forget, 2 seconds, right? So here, tell me if you want me to go back on the board. Here, the average velocity equals 6 feet over 2 seconds. Okay, so the average velocity is 3 feet per second, right? That's what I know so far. The average velocity is 3 feet per second. That's the average velocity. And since A equals A naught, V bar equals V. Now here's the subtle thing. Here's the subtle thing. Since the acceleration is a constant, then this new equation is true. In English, one of the things this new equation means is the mean velocity is the instantaneous, is the median velocity, i.e., the instantaneous velocity at half of the time. Now that's English. One reason I'm doing this problem before we do any other problems is I think this is sort of the hardest thing about that equation, V bar equals V naught plus V over 2. I'm saying that equation has meaning even before you plug in any numbers. I haven't even plugged any numbers into it, right? But if you stand back and look at that equation, it's saying the average velocity is the average of the first and the last divided by 2, right? It's saying that you could just take the first and the last, add them together, divide by 2, and get the average of the whole thing. i.e., in English, part of the implication of that is that what's the average for the whole is the instantaneous right in the middle. So the average for this whole, so I'm going to the next page. Therefore, so this is very conceptual. Like you can't see this by just plugging in. This is where physics really becomes physics, not just algebra. Therefore, what I'm saying is the instantaneous velocity is the average velocity, right? The instantaneous velocity is the same as the average velocity at, well, let me write it the other way, actually. I'll say the average velocity is the same. Just let someone in. The average velocity is the same as the instantaneous velocity at t over 2. T over 2 equals the total amount of time divided by 2, right? In other words, the middle of the time, the midway point in the time. In this case, the total time is 2 seconds. So T over 2 equals 1 second. And V average is 3 feet per second, we said. So I'm saying for my final step, step 5, FAC, I'm saying thus, V instantaneous equals 3 feet per second at precisely t equals 1 second. That's my answer, first of all. Yeah, the precise moment at which the baseball's instantaneous velocity is 3 feet per second, the precise moment is t equals 1 second. Now, I'm going to go on in a second, but I just want to emphasize like that. I don't know if you got it right or wrong. I don't know who got it right or who got it wrong. I do believe that it's possible for some people maybe to have gotten that right sort of by accident or without really knowing what they were doing. So I just want to, that's not a criticism, but just to acknowledge, like what we're really saying is this ball is not, the ball starts at rest. It doesn't start at 3 feet per second. It's not it's not going a constant velocity. It's not going always 3 feet per second. It's not going always any speed. It's always speeding up. There's one and only one moment when it's going 3. That moment is the middle moment. How do I know? Because I found out that 3 feet per second is the average velocity of this. And the average will occur right at the middle and nowhere else, as long as the acceleration is a constant. I'm going to go on, but I mean, unless there's questions, but put one final way, you'll know that you understand what I'm saying. You'll know that you really get it and you didn't get it by accident if you understand this. Question A, if I had asked it about any other number besides 3, you couldn't have done it this way. Like question A, you could only figure out the precise moment by this method. The precise moment that it had a certain instantaneous velocity, you could only figure that out because the number I picked to ask you about was the average velocity. And you had to know it was the average velocity in order to use this method. but we got that it was the average velocity by doing 6 divided by 2. I don't know if that makes sense or not. I'm going to go on to the next one. Okay, I'm just looking at the chat. Okay, there's nothing in the chat. I'm going to go. So that's the answer to the first one. Now, again, I feel like it's possible. You'll really know if you got this also if you get the second one, the second part of this correct. Because the first one, honestly, it's possible to get right sort of by accident or for the wrong reasons. But now the second question, the second part of this question, so 2b, like, okay, so for diagram and fact patterns, the same thing. Step 1, DFP, C above, right? Okay, same diagram and all that. But now, what is the question here? The question here, I keep messing up my colors, but the question is at t equals 1 second, what is x, right? That's the question here. So that's the question. Okay, now this, again, if you tuned out for the first, this you may want to pay attention because this one, people get wrong sometimes, some people. So now we're asking, remember the situation. Oh, and you know, there's one other fact in the situation that I actually forgot to put in the diagram. One other fact in the situation that was given is that the initial velocity of this whole thing is 0 feet per second, right? You know, and another fact is that it accelerates at some constant rate. We don't know the rate of acceleration, but we know this thing accelerates at a constant rate. It starts off not moving at all, and it moves faster and faster as it goes. So now it's asking us how far down the slide has the ball gotten at t equals 1 second. So it is asking us how far has it gotten halfway through the time. Now I'm going to cut to the chase right now and say, you'll know whether you want to be paying attention to this or not. I'm asking, where is the ball at halfway through the time? Let me tell you, the answer is not halfway through the space. In other words, the answer is not 3 feet for this. Let me say that one more time, just because that might get some people's attention. The answer to B is not 3 feet. Okay? I'm not going to ask who got it right or who got it wrong or whatever, but let me show you how to get the actual answer. Okay. Well, I mean, there's a couple of different options, actually. One is to practice this new equation that we derived. Well, do I want to do that first? Well, no, all right, I'm going to do it 2 different ways. All right. When in doubt, I always know that average velocity equals displacement over time, right? Here, I'm asking, and let's cut to the chase. The initial position, x naught, we've defined to be 0 already, so I don't have to worry about that. So average velocity equals displacement over time. Here, I'm asking for the displacement. I'm asking how far it gets in a certain amount of time. So I'm just going to rearrange this equation. Right? Displacement equals average velocity times time. I'm just going to rerun this. Okay. So here in this example, the time that we're asking for is 1 second. We're asking how far it goes in 1 second, right? So you might think, I mean, some people might think, well, 3 feet. I mean, its average velocity is 3 and it travels for 1 second. So isn't the answer 3? But no, if we're looking at the time, if we're looking at the time of 1 second, we want to know the average velocity for that first second, i.e., what is V between t equals 0 and t equals 1, right? This goes back to this goes back to our homework number 1, where we were saying, remember, average for a whole thing is not the same. The average value is for a given or specific interval between 2 points. You know, your average in a class after you take the first exam is not the same as your average for the whole class after you've taken 3 exams, right? Your average keeps changing. Same thing here. We have the average velocity now for the whole 2-second trip, but that's not what we need if we want to know how far the thing is going in half of the trip. So we'll have to figure it out. The average velocity, well, since acceleration is constant, since a equals a naught, then, okay, I'll write that again. Since the acceleration is constant, we can say the average velocity equals the average of the first and last velocity for the interval that we're talking about, for the interval, or a given interval. Right? So the interval here is from t equals 0 to t equals 1. So what we're saying here is, what's v naught? What's the initial velocity when t equals 0? It's 0. What is v, instantaneous v, at t equals 1? It's 3. We just figured that out in part A, right? So 0 feet per second plus 3 feet per second, all over 2. I'm saying now the average velocity for the first second is 1.5 feet per second. 1.5. So summarizing, thus, the displacement, we said displacement is average velocity times time. The displacement is 1.5 feet per second times 1 second. The displacement, so for the final answer circled, now, I just want to emphasize, something in the chat. Okay, I'm gonna look at the chat. I just want to say the answer to question 2, part B, the answer is by the end of the first second, by the halfway through the time, the ball has not traveled 3 feet. It has traveled 1.5 feet. I want to say, I'm going to look in the chat in a second. I want to say, I'm pausing on this, and I intentionally did this before Claudia's question. I'm like totally psyched to do the question that Claudia and Alan and other people asked. But it's important that I do this first because this question, the baseball, kind of like people don't always know it's hard. It seems easy, but a lot of people get it wrong. And I'm not interested in knowing who. I'm not trying to shame anybody. I'm just telling you, over 30 years of experience, people get this wrong, and you shouldn't be ashamed, but you need to know what the right answer is, and we should pause before we go on to make sure we really understand why this is the right answer. I'm going to say more about it. I'm going to look in the chat. But the first thing I'm saying, so in other words, if you're confused by this, if you're like, wait, I totally got 3, where's he getting 1.5? Join the club. Like, don't hold back, or don't be angry, or don't think you just don't get anything. Like, this is worth discussing and making sure you get. I'm going to say it a couple of different ways, but even if you didn't see this coming, like, this is a place to stop. I'm going to look in the chat, but I'm saying one more time, this ball traveled it traveled a total of 6 feet in 2 seconds, right? But in the first second, it didn't travel half of that. In the first half of the time, it did not travel 1/2 of the total distance. It actually traveled 1/4 of the total distance. And actually, the more we talk about it, the more you'll see that actually does make sense. But it often does not to people at first. So let me just look in the chat. Okay, wait. So I'm going to look in the chat. Hold on. Oh, go back a page. I'm sorry. Yes, I can totally go back a page. And it might have been more than one page at this point. Tell me if this is the right page. But cool. Oh,
I think it's like 2 behind.
oh, too bad. Okay, great. Okay, sorry. Like one more or more?
Yeah, one more.
Okay, sure. Okay. No, definitely every and
Okay.
there. Okay, cool. And take your time, and then like I'll go slowly through the other ones because I'm just going to tell you all. I just got something else in the direct chat. I got something else in the direct chat that basically says like at least one person is kind of glad that I just went over this, which I appreciate the kind words and definitely submit for points or whatever. But like really, like even if this is not what you thought you wanted, any of you, it is worth making sure we understand this before we go on. And I'm going to tell you right now too, because like this is like the fundamental, like the other stuff gets more complicated, but this is like the core weirdness of it. And once you get this, then the other stuff won't seem as complicated. But I'm going to do 2 more things before I go on. So I really will welcome any objections or anything in the chat. Again, you know, there's a big part of me that wants to say, like, can any of you like tell me if anybody feels like in the chat, even just saying like, yeah, actually I did get this wrong, but I get it now. It wouldn't insult you. It would just make me feel like I'm not wasting your time. If anybody wants to admit that, feel free. But maybe I should open up a portal for that. But here's my other point. I'm going to say one more time. Well, I'm going to say 2 things. Well, I'm going to write it. When I can turn the pages, I will turn the pages. But I'm going to start saying in English. I am saying that when half of the time has passed, half of the distance has not been covered. And that sounds like a weird thing to say. But the reason it sounds weird, but the reason I'm saying it is, if you always go through life thinking distance equals rate times time, well, let me back up. All of physics, okay, thank you, awesome, okay. So let me just analyze this for a second. What I'm saying in English, in short, is that all of physics, in a way, is an expansion and elaboration on distance equals rate times time, like that old thing. But a big lesson of physics is distance equals rate times time is like a beginning thought, but it's a very dangerous, destructive, wrong thought if taken too seriously. If you don't know what rate you're talking about, and you, et cetera. In other words, distant. Oh, okay, cool. I appreciate that honesty. Thank you, Katie. I totally appreciate. Okay. And so I'm going to say, at the risk of being redundant, I'm going to say a couple of things like, okay, note. When velocity is not constant, distance is not directly proportional to time. I'm putting them in quotes just to, because of that whole, you know, I could be talking about displacement, but just to bring it back to that expression that everybody always says, distance equals rate times time. What that makes it sound like when we say distance equals rate times time, it makes it sound like, well, if you double the time, you double the distance. And that's true if and only if the rate, the average speed or the average velocity, if that's a constant, that's true. If you're always traveling 30 miles per hour, then if you travel for 1 hour, you travel 30 miles. If you travel for 2 hours, you travel 60 miles. Like exactly what all of our parents and all of our normal people who don't take physics like think about if you're traveling at a constant speed. But if you're speeding up or slowing down, if you're changing your speed, then it still might be true that distance equals average speed times time, but then all these proportionalities that we get used to, or these linear functions, if you like, they go out the window. Well, not all of them, but the main one goes out the window. In other words, if in this case, I'm not traveling at a constant speed of 3, I'm going faster and faster and faster. So therefore, as I get toward the end of I'm covering more distance per unit time toward the end of the journey than I am at the beginning. At the beginning, so if we are speeding up, we cover more distance. We cover more distance later on in our journey. That's like I'm just trying to say it in English, later on in our journey. right? So this ball that's going down a slide is covering more and more distance per each second as it goes. That's what it means to go faster. So when the half of the time has elapsed, it has not yet covered half the distance. It's moving too slow. Now, the weird thing is, not the weird thing, but the interesting thing is, so hopefully you're with me so far. I'm saying, cool. Thank you, Alexis. Great. I am serious. Like, good. And I will move on in a minute, but I want to, very good, Katie. Yeah, I didn't even, I think that's lab 3 actually, but yes, no, you're right. It is lab 2. You're totally right. That's awesome. Yes, this is so much like this is the whole point of that. That's so great. Oh my God, I feel like I could retire now. Oh, except that then I wouldn't be able to feed my children. Okay, but yes, this is thank you. I'm going to open up a portal for connecting to the lab. Yes, this is lab 2 in the specific sense that here, in the case of constant, not constant velocity, it ain't constant velocity, it ain't constant speed, right? But what it is constant acceleration, right? It's not a constant first derivative, it's a constant second derivative. This is very much like this one. We find that x is, how can I put this? X is not, okay, let me just back up and teach you a symbol. I don't know if you use the symbol in lab 2 or not. From here on, here's a new symbol, okay? The piece of notation, we definitely use it in physics 204 as well. From now on, this symbol alpha, okay, means is directly proportional to, okay? So given that I'm going to use alpha to mean directly proportional to, then in the case of constant acceleration, position is not directly proportional to time, right? If you double the time, we didn't double the distance. Or if you took half of the time, we didn't cover half of the distance. But what x is proportional to, here's the connection to lab 2, like Katie just said. I'm really psyched that she said that. What we find is that position is directly proportional to time squared, right? Now, right? Like in half of the time here, in 1 second, the ball didn't cover half of the distance. It covered exactly 1/4 of the distance. It's right, and 1/4 is the square of 1/2. This is not a coincidence. Especially if you understand your calculus, or if you're starting to make the connection to calculus, what we're saying here is we have a constant second derivative. The second derivative is sitting there in a second degree polynomial. X is not proportional to t. X is proportional to t squared. How proportional to t? What do I mean by proportional to t squared? I mean that equation that I derived in the other section or on the videotape. Oh, sorry, let me read it all fully. X minus x naught. Although again, here x naught is 0, so don't let it stress you out. The x naught, like in this case, it's 0 anyway, so don't pay too much attention to it. That equation, which came from just algebraically shoving 2 other equations together, or that equation, if you're getting comfortable with calculus, or if you are comfortable, you might notice this equation, take one derivative of it, and you get AT plus V naught, right? That's V equals, well, should I do it? Yeah, I'll do it. Note, V equals dx dt equals, I'm doing this a little bit fast. This will make more sense to some of you than others. That's okay. But look, right? If you take one derivative of this equation, you get instantaneous velocity, right? If you take the derivative with respect to t, use the power rule is what I'm talking about. You get AT plus V naught. That's just a rearrangement of an equation we already had for acceleration. And if you take another derivative of it, the second derivative, you get just A, right? A, the constant A. I'm trying to say that when you have a constant a, what you have is a constant second derivative. So the equation it produces, even though I used algebra in the last class to derive this, you could just see it from calculus. What we're saying is when the second derivative is constant, position is not proportional to time, it's proportional to time squared. If you see the pattern, you could imagine, and I think this is part of lab 2 also, if we had a jerk that was constant, like me at the front of the room. No, if you have a jerk that's constant, if you have a, and I'm going to say this for any of you for whom it lands, and if not, don't worry about it, and I'll move on. But like, if the rate of acceleration change was constant, if the third derivative were constant, then the equation would be like 1/3 jt cubed plus blah 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 blah. Right? That's how derivatives work. This is a quadratic function of time. So here's the last thing, and then I swear I'm going to move on. But just so you could see this, so this equation really does actually make sense. This position function that we use for constant acceleration, we could have used it in this problem. I initially solved this problem without this equation because we're just getting used to this equation now. And I want to show you that everything makes sense in physics. Like even if you don't know this equation, you could still solve from fundamentals. But this equation, now that we have it, is a shortcut. So what we could have done, I'm going to do this really quickly, just so you see how it works. And then we're going to move on to, well, for 13 minutes, we're going to start with Claudia's question and Alan's question and Eric's question. We're going to start. We won't get to all of it, but then we're going to just continue on Monday. And again, you don't have any new homework, so forgive or bear with or whatever or celebrate. So shortcut method to this shortcut method to problem 2 part B, which was at t equals 1, what is x? Well, we could have just plugged in, and maybe some of you did. We could have just plugged in to this new equation we have. We could have plugged into x minus x naught equals 1/2 at squared plus v naught t. The x naught is 0. Okay, here's step 4. Step 4, PAW. We could have just plugged in and we would get x equals 1/2. Well, okay, we would get x equals 1/2 a 1 squared plus v naught times t. What's v naught? It was 0. So we just have to do 1/2 times a times 1 squared. But what is a? And again, this could happen to you on an exam. You write down an equation, you're going and going, and then you're like, oh no, but I don't have A. What you don't want to do is say, oh no, I don't have A. That means I'm doing the wrong thing and then cross everything out. No, if you're doing stuff and you're being methodical and now you realize you don't have A, so you just stop and see if you can solve for A. I think we can. A, and we will. A equals, like acceleration is change in velocity per time. Now, I could use any time interval I want for this because the A is never changing, right? It's the same A all throughout. So what do I know, for example, I know that the velocity at 1 second was 3. The velocity at 0 seconds was 0. I know that this ball took 1 second to accelerate up to a speed of, or an instantaneous velocity of 3, right? That's what I already figured out in part A of the problem. That's where I got these numbers. And again, I understand some of you could do this in your head, that's fine, but just for those of you who can't, and I don't think I could, I mean, I can now, whatever, you understand what I'm saying. So A equals 3 meters per second squared, right? It takes 1 second. And I could have, well, anyway, A equals 3 meters per second squared. Therefore, thus, x equals 1/2 3 times 1 squared. So again, there's that squared. It's proportional to the time squared. I get 1/2. Well, here. So let me be careful about my units as long as I'm doing this. Sorry. 1/2 3 meters per second squared times 1 second, right? So 1 of the seconds cancels, and I'm left with Sorry. And all that is squared. So all of the seconds cancel. This is squared. So all of the seconds cancel. And I get 1.5 meters. Okay. Now I know I'm starting to run out of time. Again, I'm very, very psyched that Claudia and other people specifically asked for a question. I will start it. I won't finish it, but I definitely want to honor it. But hopefully this was helpful to some people. Last thing on this. So the answer is 1.5. Now I remember also, it's possible that some of you just plugged into the equation and just got this answer. If you just plugged into this equation and got this answer, then you got it right. And that's cool. And that may be what some of you were saying in the chat, like I don't remember what I did, but this helps me understand. Right. It's possible that some of you got the right answer, but didn't even look at it long enough to realize that it's a surprising answer. So I want you to see two things. I want you to see on the one hand, it kind of is surprising, but on the other hand, it really does make sense. But that's what plugging and chugging into that shortcut equation now does for us. It forces us to realize that position is directly proportional to time squared whenever there's a constant acceleration. Okay, I'm going to do my best to do whatever I can in 8 minutes on the question, Claudia. And I'm just keep on using her name. I'll use anybody's name who asks for stuff. Okay, so 3. So I'm going to skip to 3 now just so I can start it. Well, that doesn't mean it's the only thing I'm going to do. 3. Oh, 3. A few balls. Oh, yeah. Good. Yes. Okay. Now, the thing about this, so a few bolts. Yeah, this is hard, and this is worth talking about. I mean, it's not impossible, but it's hard. It's worth talking about. However, one big thing about this problem is there's many ways to do it, but it's a heck of a lot easier to do if you start getting used to this equation that I just established. I would definitely use the 1 FAT squared equation for this. Also, remembering lab 2 and picturing lab 2 is meant to be very helpful for this. So, okay, we'll see how far we. All right. Okay. So a bolt gets dropped. Okay. And its initial velocity is 0. Okay. But then 5 seconds later, another bolt comes. So this is at t equals 0. And then this other bolt at t equals 5 gets thrust down at 40 meters per second, right? So they're not at the same time. And I'm going to say again, just like before, I'm going to call down positive. I'm going to call up negative because everything is going down. There's no point in making down negative. I'll have a million negative signs. Okay, there's 40. Okay, so that's all the facts. Okay, so that's DFP. So then question A is how large or small is the gap, the distance between the bolts at the instant 2 more seconds elapse? Okay, so what we're really asking here is at t equals 7, if you see what I mean, right? It says 2 more seconds. So we had t equals 0, then something happened at t equals 5. Now it's asking 2 seconds later what's going on. So it's asking about t equals 7. And what it's really asking is, let's say, what is XA minus XB? That's what it's really asking, okay? And I think even if I don't finish this, I can at least set this up for you in the 5 minutes. But I think the question is, what's the difference in position between the 2 bolts 7 seconds later? And I'm calling down positive. So if I get a positive answer for this, that will mean that XA is farther down than XB. If I get a negative answer, it means B is farther down than A. We can re-summarize that, at the end. But this is what I'm really asking. How can I get it? Well, the fastest or the most direct way is basically to solve for X for each one separately and then just subtract. In other words, XA equals 1/2 A of A T squared of A plus V naught of A T. Right? They're all starting at the same height. So let's call that height, that initial height, we're going to call 0. They're all starting from the same place. So I can call that initial height 0 for all of them, right? So I'm not worried about x naught anymore. Like minus x naught, it crosses out to 0. So I'm going to just solve for xa, and I'm going to solve separately for xb. I'm going to use the same equation. I'm just going to plug in the different values for each one, and I'm literally going to subtract. That's what I'm going to do. Hopefully I'll finish it right now, but that's all I'm going to do. So I'm doing it a little bit quickly, obviously. So xa. So xa equals 1/2 a. Well, what's a? They're both, this is from lab 2. Approximately, they both go down at a rate of 10 meters per second squared. That's rounding. You can call it 9.8, but it's calling it 10. That's fine. Physicists do that all the time. And it's positive because I'm calling down positive. So xa accelerates down for a time of 7. Well, hello. Of 7 seconds, right? Because it was already moving for 5 seconds before the other one started. So it's going a total of 7 seconds, and it's dropped from rest. So xa is 5 times 49. I'm going fast here. I'm like leaving out the units that's sitting here, but you could check the units. So it's 245 meters. That's how far down bolt A falls. What about bolt B? This is, now we have 3 minutes. I'm just going to do this one and we'll stop. But, well, I think. But B, same deal, 1/2, same acceleration, 10 meters per second squared. But this one's only going for 2 seconds, I believe, right? For 2 seconds. And it has an initial velocity of 40. So we plug, in other words, this was 0 times t. So I left it out. But this one is 40 times 2. Right? I'm just plugging in the different facts for the different bolts. So this one is going to be 5 times 4 is 20 plus 80. So XB, this is 5 times 49. So XB goes 100 meters. So I think the answer is XA minus XB is 145 meters. I think that's the answer. I think the top bolt, in other words, is goes 140. The first bolt, bolt A, goes 145 meters farther than the second bolt. It has more time to fall. Well, I'll analyze why maybe next class, but I think that's the answer. Let me just look in the chat. I know we have like 1 minute. Let me just. Go back 1 page. I'm sorry. Yes, I can go back 1 page. Oh, yes. Whenever it says draw a graph, that's a good question. Yeah. Desmos. Yeah, I'll never say no to Desmos. Yes, you can use. Sometimes it's really good to also get in the habit of sketch, but sure, my fast answer for now is sure, you can use Desmos. Yes. I love Desmos. Okay. I know it's 1:30. Hold on. Let me just look. Tell me whoever asked me to. Oh, great. Okay. Let me just, I think we can. Oh, that's why you asked. Yeah. I'll say this quickly. We're going to stop here, but the velocity time graph, whether you use Desmos or use your hand, you'll know you're doing it right if your graphs should be straight lines. If it's a velocity versus time graph, velocity versus time, those will be, you'll have 2 straight lines. They'll have the same slope. The slope of both of them will be 10 meters per second squared. Okay, and depending on how you define your axes, you'll have 2 lines that both have the same slope. They'll just be parallel to each other. One will start at 0, 0. The other will have a y-intercept of 40. And that's the only difference between the two of them. That's the graph. So I'm going out of order, but I'm going to stop here. So the graph would be 2 parallel lines, 2 parallel straight lines, one with a y-intercept of 0, the other with a y-intercept of 40, because that's its initial velocity. And they both have a slope. If you look at your scales, they'll both have a slope of 10, because that's the acceleration. That's the answer to C. The answer to B is the gap, the distance between the two had better be getting larger and larger, because one of them is going faster and one of them has velocity relative to the other. One is going faster than the other. Therefore, it's going to be going farther and farther per time than the other. So, okay, we'll do more. We'll pick up on this on Wednesday. Just you catch up, I'll catch up. Hopefully this is at least making some sense. Hopefully you feel like we are going faster, but not too fast. You'll let me know. But have a great, and I'll hang out for a second for any questions or whatever. But other than that, have a great weekend. Have a nice day. Yes, thank you. Thank you. Great. Have a great, yes, have a nice weekend or a nice week. Yes, have a nice, thank you. Awesome. And I'm hanging out for any questions. I'm also going to turn off the recording.